about, we're going to try to do three things. That's perfect. And let me agree so I can see. Yeah, three things involving streams and dark matter. It's kind of ambitious, so we'll see if I get through all of it. But I'll start with some introduction. So this is going to be all about tidal streams, in particular, globular cluster streams for the most part. So this is what happens when you take a satellite galaxy or a globular cluster and you chuck it into a more massive host, and it begins to leak out stars primarily through its inner and outer Lagrange points. It gives you these distinct tidal tails. And you have a lower energy leading arm and a higher energy trailing arm, and they extend out over a long range of orbital phase. And what's so useful about streams, why they've been used pretty extensively over the years, is that they more or less trace orbits. So you can look at the parent orbit in blue of the progenitor, compare it to the track of the tidal tail, the little points, and they more or less follow a series of similar orbits, which is very useful because in the outer halo streams, the timescales are easily hundreds of million years. So streams let you more or less see orbits in the outer halo. Observationally, the latest Gaia data release and previous ones as well gave us this incredibly rich data set. So there's over 80 streams in the Milky Way. Some of them have full 60 phase space measurements. These are the 3D positions of streams. And what you can think about starting to do with such a rich data set like this, and what has been done in the past, I'll talk about some previous work there as well, is try and learn about the potential of the Milky Way and other galaxies. So the question would be, how does the morphology and kinematics of a stream change if you vary the mass distribution of a galaxy? So this is just an orbit-based example. You start with the same sort of final condition and you integrate back in different mass distributions. Of course, different mass distributions mean different orbit families, and streams are going to trace those different orbit families and let you see them. So they're sensitive to the overall potential. But I'm also going to talk about local fluctuations in the potential. So what happens if you take a stream in a galaxy with a rotating bar? So this is based on a real Milky Way stream, Pal 5. We can play its orbit forward. It hits the bar, compare it to a static bar scenario, no time dependence. You see that there's some differences, but we can zoom in. Static bar case, rotating bar, very severe scenario, but it gives a sense that streams are very sensitive to orders of magnitude and mass scales, and also time-dependent mechanisms going on in the galaxy. So my thesis work has, making this talk, I didn't realize that the whole order of magnitudes and mass scale before, but it really has gone all the way down from 10 to the 5, maybe to 10 to the 12. And my hope is to talk about 3 of these topics here. So we'll be sampling this mass line. But the common theme has been, how do you take observations of streams, be it in density or kinematics, so on, and learn about something with the dark matter. And I'm going to start with Milky Way potential reconstruction. So what we can learn from the Milky Way using streams. So how do you measure the potential with streams? You saw that orbit-based example before, but just going in a little more detail here. Let's say you observe a stream. This coordinate frame is going to show up a lot. This is just an analog for RA and DEC. It's just a rotated ICRS coordinate frame. And you adopt a potential model. There's many options you can pick, right? And then you do some sort of MCMC, where you generate a bunch of tracks and you compare your model to the observations. So this has been done a lot. This is just a subset of, over the years, different takes and attempts at trying to measure properties of the Milky Way with streams. And there was a recent review paper that very conveniently tabulated a lot of these measurements. I'll highlight the stream-based measurements here in blue, the little circles. And you can see for enclosed mass, to pretty good precision, we have some sort of convergence on the enclosed mass of the Milky Way. So that's one thing that looks good. But what about the shape of the halo? What if we go to like the next resolution level up? We can look at the flattening. So you can think of this as like C over A. Q of 0.5 would be very oblate. 2 would be very prolate. So how squashed is the halo? And there's a pretty significant amount of variance. There's not a clear picture from streams, at least, and other observables as well, of what the Milky Way halo looks like beyond the mass enclosed. So why might you care about that? Well, for one, it's good to have dynamical models for the Milky Way, so you can do dynamical things, right? So if you have a sensitive model that cares about the shape of the halo, you want to get this right. On the cosmology side, of course, cosmological simulations predict just about everything. And one of those things is the axis ratios. So we would like to know, where does the Milky Way fall on this sort of C over A histogram? Is it sensible? So what might be going on? Unfortunately, I'm not going to give you the answer. I don't know, but maybe working towards it. One thing that can go wrong is, what if you have the wrong model? What if you do this like generative approach, but you pick the wrong phi, the wrong potential model to start with? So sort of contrived example here. Let's say I take that same stream as before in black, take that as the observations, and then we'll try to fit it with an axisymmetric model when the true potential was slightly triaxial. So a bit of a departure from axisymmetry. The green is the best fit that I get out. Not bad. There's definitely some discrepancy, but it would be small discrepancy. It would be not anything that would necessarily say that this model is horribly wrong. But of course, you're forcing it to be axisymmetric, so you haven't totally uncovered the mass distribution. So it's sometimes hard to get the model right if you want to get a perfect fit, right? So one idea that I'm going to launch into next is, what if we can sort of bypass this step of having to write down a potential model and do things in a way that's more agnostic to the functional form of the potential? So what if we can go basically to accelerations? So how might you do that? You have to make some assumptions, and this is going to motivate what the main assumption is. So I'm going to take an n-body stream here and basically just slide along its energy and angular momentum distribution. So I'll let that play. And what you see is, with the exception of right there, things are very smooth and well behaved. There's a gradient in energy in LZ. And in this potential, at least, energy and angular momentum are constants of motion. So one orbit would be just one dot. So you can see there's a mixture of orbits. But the mixture of orbits is well behaved. So as you slide through phase angle, things aren't changing very frequently. But again, it's not a perfect orbit. What's going on in the middle there is the progenitor, where the cluster has self-gravity. So in that area, energy and LZ are not constant, at least in this fixed potential. So streams are a mixture of orbits that vary slowly. So here's a very schematic picture of a model that is totally data-driven. You have your stream. Little particles are moving along their velocity vectors, and we can highlight their local tangents. What that last plot was motivating, that locally the orbital mixture is similar. Locally things are co-moving, but distinct segments of the stream are not co-moving. So that means if you can trace through all of these local tangents, sort of go downstream and derive a position function that's a function of the scalar parameter that'll pop up a few times. It's like an angle, just arc length, whatever, gamma, and do the same thing for velocity. It turns out that once you have your model for position and velocity, and you have this local orbital mixture condition, then you can actually back out a potential, or sorry, an acceleration, without ever having to write the potential. So that's the point. You can get to A without ever having to specify phi. And what that equation looks like is like this. It's kind of just an application of the chain rule differentiating in gamma to eliminate time dependence. But all that it's saying is essentially almost a continuity condition. It says if you change your velocity by this much and your position by this much over an increment gamma, then that implies an acceleration of that. That's what it's saying. It's not well regularized. So one thing you want to do is ask that your mass densities are positive. So that's from Poisson's equation. That's something that I'll mention in a moment. So we'll try to bake in a condition that regularizes this expression. It says nothing about the acceleration being like curl-free or conservative. So how does this work in practice? You take data and you color code it by some phase angle here, or you order it, and you just fit tracks. So you just fit a track in 60 phase space, very simple. You apply that equation that you saw, and you get out something about accelerations. In practice, we add this like physically motivated prior, which basically says we want smooth accelerations. So we try to fit a track through the data that gives us smooth accelerations and is compatible with the 60 or the 1D curve in 60 space. So that's the sort of basic idea there. So we've done this pretty extensively on simulations and known potentials, but we don't tell the model the potential, of course. So this is an example fit. Doing it for 6 streams, the output that you get out is something like this, where the x-axis here is that gamma parameter, angle along the stream. then the y-axis are the 3 acceleration components. So black is the correct answer and red is what you get from this approach. What is the gap? Why is there a huge hole there? It's just because that's where the progenitor cluster is, and around the progenitor, because you connect through the leading and trailing arm, you have that S shape, you don't want to fit that S shape. That violates the assumptions that we're making. So if there's a non-dissolved progenitor, you want to be careful in that region. That's what this is doing. So that's, yes.
How do you know where gamma 0 is?
In this case, it is scale. That's how I choose gamma. I choose gamma such that where the progenitor is located, I say that's going to be gamma of 0. For real data, sorry?
You know the progenitor.
In the simulations, yeah. In real data, there's maybe like one such stream where we'd have to worry about that. Yeah, I'll get to that in a moment. But the good news with this is once you have accelerations, you have the fun of trying to interpret them as a post-processing step. So now you can say like, okay, my data are this set of accelerations measured over the stream, and I want to find the density or potential model that reproduces the data. So again, this is the case where it's simulations and we have the right answer and you sort of get the right contours back. Okay, so real data, very recently, this was hard to do, I think, until recently, because we require this 6D phase space information. Relatively recently, Nathaniel Starkman and I have a paper where we're trying to get stream members from the GD1 stream. This is a real Milky Way stream, as seen in Gaia and Pan-STARRS. And we model the photometric distribution, we model the on-sky distribution, and we get membership probabilities for each star in the field. So this is sort of like the ideal data set to do this sort of thing. So we can take this information. Gaia doesn't give us a ton of RVs for this, so we take a recent paper, very recent, that gives us a radial velocity track from DESI of the GD1 stream. Data look something like this. What's going on here? This is the distance modulus from the DESI paper, Monica Valuri's paper, derived by the subgiant branch. They use it as a standard candle and back at a distance modulus. It is in very good agreement with other works. You could definitely argue that the exact like functional form and shape of this distance curve, maybe we should add more uncertainties, that's fair to say. But we have a good first pass to what a 6D view of GD1 looks like with many tracers. Okay, so we're going to fit curves to this and have the scary moment of truth where we look at what the accelerations look like. So totally data-driven, 1 sigma, 2 sigma errors here. The y-axis is kilometers per second per megayear. So we're measuring changes up to like 1 kilometer per second per megayear. This alone means nothing. We have to compare it to other constraints. So the first pass, like easiest thing to check, is a very common model for the Milky Way. Simple, it's a 3-component model, disk, halo, and a nucleus or a bulge. And it's derived from rotation curve data and local equilibrium modeling in the plane from Joe Bovey in 2014. And we can look at where the different components of that model land on this. So here we have the disk, we have the halo, and then the total. The bulge doesn't contribute really anything in this plot, so I'm not showing it. But I think it's pretty remarkable. Totally data-driven, we get very similar and sensible values for the acceleration with some disagreement, which I will now dive into further. But I think the total mass enclosed is almost exactly the same within like 10%, let's say, or lower of Bovey 2014. So again, like this mass enclosed thing is being well measured and consistently. But you see there's some disagreement, and I'll get back to that in a moment. Very conveniently, in Bovey's 2016 work, they look at the same exact stream and use a totally different method based on actions and angles to try and fit GD1. And they provide this great plot where they're showing the cylindrical R force and the z-axis force as measured in the vicinity of GD1. And when they combine that with a prior from other measurements of the galaxy, they get those black contours. And then, of course, we also get out FR and FZ in the cylindrical frame from our model. Very consistent. Everything is lining up sort of with what you would expect. Another geometry thing that you can do is if you assume that the potential looks something like that, you don't need to know its functional form to say what the flattening is. So taking some derivatives of that function, The flattening is that quantity in the top right. So we can see what that looks like as well and compare it to prior work. So what we find, the caveat here is that this is the total flattening. So this includes like baryonic and dark components as well. We get something like 0.9, which is very consistent, nothing surprising or unusual there. But I think it's a kind of a nice story that we're finding consistency with generative models that people have used a lot over the years. Whereas this is a totally different model. We're making completely different assumptions and not relying on the same approach. So that's where things all agree. If we read into it a bit further, like I said, you can see that there's some discrepancies here. Of course, I'm just showing you a point estimate of Bovie 2014, but not everything's perfect. And the main thing is this A phi. So A phi is the azimuthal force. If you have an axisymmetric potential, A phi should be 0. We're consistent with 0 all the way across. You can see we have like a 2 sigma discrepancy around the center of the stream. Why is it around like -40 and why did the arrow bars blow up there? It's because we're fitting these flexible spline tracks to the data. And at the ends of the stream, it's very uncertain like how to draw your spline. So the posterior distributions are very wide there. That's what's going on there. But it's then makes sense that towards the center of the stream, that's where your track is like the best defined. Okay, so now we want to interpret this. What does this A phi non-zero suggest? So we can MCMC it and fit an ellipsoidal density model. So just think of an ellipsoid with a disk and a bulge. And we're going to allow that ellipsoid to rotate, and we're going to allow it to be triaxial if we want. I'll tell you, I'm sort of glossing over the density and mass enclosed because it's all very consistent with all the previous works that I showed before. But we can look at the best fit density, and it's actually quite axisymmetric if you're in the frame of the principal axes, like C over A at 0.8, but it's tilted by something like 40 degrees. So if you've been following the literature on halo shapes, which is maybe a niche thing, but as I showed you before, there's sort of like a very wide range of discrepancies on these values. But relatively recently, there was an H3 paper which reported that if you measure the distribution of stars from in the Milky Way and the halo, so mostly GSE stars, these are stars that came in with the merger like 8 gigayears ago, they are in this ellipsoidal shape and tilted by like 30 degrees roughly. So it's very easy to make these same plots and say, it looks kind of similar actually in YZ and XY. But again, this model is very axisymmetric. That's why these two look exactly the same. This is about, as much as I wanted to show here, but it seems to be sensible that there's a few dynamical tracers now, Sagittarius as well, that Nant has worked on. He has a paper on this, that seem to suggest that the halo might be tilted, and in some cases triaxial. And I find it intriguing, but I don't want to go further than that the YZ projection here looks similar, though also kind of strange that the tilt here is non-existent or maybe even in the wrong direction. So does that make things any better? I'm not sure. But at least looking at the various literature sources here that allow for a tilted halo, our constraint here is this. Maybe there's some convergence. It's interesting, this Kopasov 23, there's a degeneracy where you could have an oblate and a perlate halo. But at least it seems that a few of the inner and outer halo streams of the Milky Way are much better matched by this tilted halo. Maybe the H3 data suggests the same thing. So we're going to have to do more to figure out, what the right answer is. But I think maybe there's some convergence that's starting. Okay. So that's what I wanted to say about Milky Way potential reconstruction. This next thing is actually very much related, but we're just going to remove data and think about extragalactic streams. So again, you saw this plot before, Milky Way streams, you get this full like 3D 60 phase map, lots of data, but it's very different in external galaxies where you just have images. And we're going to get a ton more images with things like Rubin and Roman are going to reveal a lot of the low surface brightness tidal features. We're expecting to see like easily tens of thousands of them. How many are streams and shells is maybe a little less certain. But here you just get an image. Maybe you get some surface brightness information. And a central question you can ask is like, what do you do with this? This is very hard to forward model because you have so many of them and there's so many projection effects, right? It's a complicated sort of like simulation-based inference problem. How do you go from the image to maybe some science result or some constraints? And one way to think about this is just take the stream as you see it in the sky and think about the accelerations that the stream is feeling. So like the planar accelerations. You have a component of acceleration that's along the track and one that's perpendicular along this curvature direction. You don't have to read into the equations now if you don't want, it's not crucial. But the main thing that you get from the equations is looking at this expression, the perpendicular acceleration has a halo model component. So what is the perpendicular acceleration? Where is it pointing and what's its magnitude? Then it has this observable thing, which is what direction is the stream curving in? Is it curving down? Is it curving up? It's like a binary question. That's a lot of honestly unnecessary math to say. All this means is that the stream's curve and the acceleration that it's feeling in the sky should be within 90 degrees. If it was anything greater than that, it's going to go in the opposite direction. Very simple, actually. So halo models that violate that principle, you can sort of cross them out. That's the idea. And we can run some n-body simulations and look at the accelerations evaluated along the stream here. That's the green arrows. And just sort of eyeballing it, you can see, yeah, makes sense. It would be weird if it's not true. Acceleration and curvature are compatible, at least in these static models, right? Next level up is going to like fire simulations, which we're thinking about soon. But here's a test where we're going to look at 3 streams in an oblate, perlate, and spherical potential in the middle. And a way you can visualize this acceleration curvature thing is for different halo flattening, so that same hue that's showing up. Do we ever sample a model that is completely in this allowed region where curvature and acceleration are within 90 degrees? And if you pass into that like forbidden pi over 2 region, you cross out that model. And then we write a likelihood to like characterize how successful each model is. Sometimes you can get a very surprisingly tight constraint. There's interesting features of the stream that give you a tight constraint, particularly if it samples a lot of curvature directions. It's hard to find a good model. So you sort of like narrow the parameter space down. Also, if there's a straight segment along the stream, that will tend to suggest that the acceleration is not pulling the stream away and left or right. So that helps too. Sometimes you really can't say much at all. But other times, right, you get something modestly, informative. So we can go ahead and try this pretty simple analysis with a real stream, sort of as a pilot study. This is NGC 5907. It's at 17 megaparsecs. And we're going to allow the flattening of the halo and the disk halo angle to change. So like the flattening direction and how much flattening is going to change. We draw our track, lots of splines, just like before. We sample these 2, and pretty remarkably, the best fit, I'm not showing the full posterior here, right? This is just the MLE, but the MLE is very much consistently aligned with the disk and very squashed, very oblate. The model knows nothing about the disk. This would be total flattening, but just the stream's shape and overall morphology suggests that you have an oblate potential that is overall well aligned with the disk. And then you can run a forward model as well and ensure that it's working how you think it is. So that's always available to you, but it's just more expensive. So it's nice to have faster methods. Again, like why do this? I think this is a prediction of CDM that is very underexplored because there's not a lot of tracers, but we would like to measure the flattening distributions and like disk halo angles for lots of streams. It's hard to do. Like if we're going to have tens of thousands of tidal features, I can just sit here and like trace all the tracks because that's a lot of work. So one thing I've been thinking about a little with Nathaniel Starkman and Sarah Pearson is how to do this in a faster automated way to sort of fit tracks, get halo shapes, and then compare to simulations or whatever science case you might want. Very like preliminary recent news is we are starting to work with the Galaxy Zoo team. So this is typically the Galaxy Zoo folks will do morphological classification of galaxies using input from citizen scientists. So they'll do things like trace spiral arms and bars. Why not streams as well? So the idea, very pilot study here, is we can take data, and these are Nathaniel's tracks that he overdrew. And if we can get like thousands of citizen scientists to do this sort of thing, we get full distributions on tracks. And we can try and propagate like the uncertainty on the track through and see what that does to our constraints if they survive, right? Because the hard part here is like, how do you draw a good track? That is definitely a caveat. But I think it would be good to have a lot of input. Maybe we can train some ML models to do that as well once we have a good data set to start with. So the final thing here that I wanted to focus on is the lowest mass scale, focusing on subhalo populations. So here we're zooming way in. So we just went to the biggest scale in this talk down to the lowest ones, back to local fluctuations, thinking about which one of these pictures is correct. Is it cold dark matter, self-interacting, or warm dark matter? Different dark matter models predict a different amount of clumpiness in the halo, particularly in these dark matter subhalos, which are expected. Some of them are going to be completely deficient of any stellar component. So we expect like 10 to the 6 free floating subhalos that don't have stars in a CDM universe. And we expect that those subhalos, because streams are so sensitive to basically everything, are going to interact with streams and lead to gaps and other things like density wiggles as well. And this is 3 cases of real data where you can see that basically every time you look at a stream with enough resolution, things look like pretty different from smooth. There's departures from the smooth models that you expect in a static, simple halo model. So what's going on? It's like a big problem of whodunit, basically. Where do the density variations come from? I already mentioned how PAL5 can feel the effect of the bar. So in the literature, it's been proposed that the asymmetric tidal tails of PAL5 can be explained by it being in resonance with the bar. GD1, seeing this a few times now, but it has this gap in bifurcation, which is very well modeled by an interaction with like a 10 to the 6 solar mass subhalo. One thing I haven't mentioned so far yet, I think, which is surprising, but the LMC is like the biggest subhalo in the Milky Way in a sense, and it can also have a very outsized effect on streams. So the OC stream, you have this scenario where the proper motion vectors along the track are pretty severely misaligned with the stream itself. This would be an example of that track analysis that we started with, where you would not want to apply this. That violates that energy sorting assumption. That stuff is better for inner halo streams, but outer halo streams care about the LMC. And we talked about the bar, even, unsurprisingly, I guess, the overall disk matters too. So how the disk started to form and evolve in angular momentum over several gig years can change the width of streams, make them unusually narrow, or make them fan out as well. So the point of this picture is to say that there's a huge scale of forces, literally, that are shaping streams. And we want to know about the small scales because it's important for competing dark matter models. So this is a difficult problem if you think about how do we say which of these density variations are due to baryonic things versus subhalos. Just thinking about like a thought experiment where you have 100 subhalos that maybe intersect with a stream, and you don't know which one of them are on and which are off. So what is like the presence and absence of this set of 100? It's a really terrible combinatoric problem that if you imagine having to do a bunch of brute force simulations, you're not going to cover the full sort of solution space. But if some of the subhalos or most of them are lower mass and you can treat them perturbatively rather than doing like the full simulation, basically just like Taylor expand the simulation is the idea, then you have the freedom to scale up and down algebraically the strengths and presence and absence of each subhalo. That doesn't solve like the combinatorial problem, but it makes it way more efficient to apply things in like linear regression, which are very fast. So that's something I've been working on recently, where we're essentially just treating a stream as an ensemble of test particle orbits and applying perturbation theory consistently to all of them as you have a subhalo flyby. And what's good about this is you can include whatever you want in your baseline orbit. So before you point your finger at a subhalo, you can say, all right, I want to include the LMC, I want to include the bar. Maybe you have some like semi-analytic GMC treatment in there as well. And then a subhalo flies by and it distorts your orbit. So it gives you a sort of velocity kick that changes how the orbit will evolve in phase space. And maybe the subhalo had a bunch of different masses, let's say, like we don't know if it was 0 or like 10 to the 6, whatever. You get these series of nested curves. And the idea is that as you vary the perturbation strength, it would be nice if we can like hop from curve to curve very efficiently. So how can you get that? You take derivatives. You take derivatives of your phase space with respect to the perturbation parameters. And if you have these in hand, then you can literally just do that rescaling, get the derivatives and then put them up and down. I'll show an example in a moment. You can do a little math to get out an equation that just in general terms tells you what at least the velocity derivative looks like here. It's pretty intuitive, actually. It tells you that there is force that is imparted by the subhalo on the particle. And then you have the tidal tensor of the galaxy. And that part says, well, if you get knocked off your orbit, that changes how you subsequently evolve. That governs like the phase mixing after your perturbation. So what does it actually look like to do this? Enough of the nice animations. I guess here's another nice animation. But nonlinear perturbation here, there's a 10⁶ solar mass subhalo that hits the stream. It leaves a very tiny density gap. Nothing huge, but maybe you can see it up top better. And I'm just going to turn on the perturbation strength of this one subhalo, all algebraically. And you can think of all these stars as being on a little track that follow the red vectors. Once you reach 10⁶, you get a pretty good match. Then eventually you go outside of the nonlinear regime and you break the stream and break the model. So it works up to typically like 10⁷ solar masses. We have some metrics that tell us like when we've left the nonlinear regime. But within the nonlinear regime, this is like a huge advancement in speed, just being able to like tune all these knobs. And I'll try to show you in a moment what we can do with that. So I guess a little more on the motivation part of this. I showed the picture before that different particle models for dark matter have different predictions for the number of subhalos in a mass bin. So this is like the mass function for CDM that goes all the way down to very low, even like Earth mass subhalos. And then warm dark matter and fuzzy dark matter, they have cutoffs as two examples here. So if you change like the particle model, you change the number of subhalos in each mass bin. So if you take this black curve and you basically take like a scattering experiment and ask how many subhalos should hit the GD1 stream that we've been looking at a lot, you should get something like 100 total impacts going down to 10⁵ solar masses. One of those impacts under CDM conditions fit from cosmological simulations are going to be quite massive, above 10⁶. The wide majority of them will be under 10⁶. So we looked at one example with a single impact, but in this regime of 100 impacts, what I'm going to do here is hit the stream 100 times. One will just be unperturbed static and the other will evolve. And I'm just going to scale up and down those perturbation amplitudes up to like a CDM level, then back down. So you can see what happens when we do this. So the main thing is this bifurcation that you get out when we reach peak mass, like right about here. But the other thing that's happening is how diffuse the extended tidal tails become. So sort of unsurprisingly, if you like inject all of these random forces with lower mass subhalos, you get these velocity kicks, things get diffuse and hotter. That's what's happening in the extended tails. So what this says is like the lower mass subhalos qualitatively will tend to heat the stream. So they increase the velocity dispersion and the width. The more massive things are what give you your gaps and bifurcations. The gaps and bifurcation point has been covered a lot, I think, but now that the data is getting a lot better, we can really think about velocity dispersions a bit more. So focusing on velocity dispersions, we can start to do experiments where we look at the binned radial velocity dispersion at a function of angle along the stream and basically just vary the impact rate. So if this is like, 100 impacts, this would be 300. And you can just scale up and down the total number and see how the velocity distributions respond. And we can take real data, which is centered at like a 20-degree segment on the left part of the stream here. We're going to use data from MMT. This is a view of GD1 in radial velocity. I can update this plot now. I think with the earlier one, we have more stars, but starting with this 43, you can go out and measure high precision RVs for GD1 and get out something like 2.3 kilometers per second for the velocity dispersion over that segment of the stream. Interestingly, if you take your best pass at like a direct n-body model in a static Milky Way potential, so that's a caveat to think about, you get a much lower velocity dispersion of like 0.6 and 0.8 kilometers per second. So one question you can ask is, how do you explain the discrepancy? If we wanted to point our finger at dark matter subhalos, like how many subhalos would it take to explain that discrepancy and fill the gap there? So that's what we looked at here. We can look at histograms of how much velocity dispersion does a population of subhalos inject in a GD1-like stream, just scaling up the rate of impacts there. So again, as I've been saying, more impacts, more heating. Just from CDM alone, you get something like just short of 2, but remember this is injected velocity dispersion. The stream also has an intrinsic dispersion that we'll need to add on top to see, where the data falls. You can do the same thing for the concentration of the subhalos. So we also do that perturbatively. So we vary both the mass and the radius of all the subhalos. This story makes sense too. If you make the subhalos puffier, they give you less heating. So you sort of move leftwards on this plot. If you make them more concentrated, but at the same rate, you move rightwards. So there's definitely like a rate concentration degeneracy here. So what we do now is basically use these distributions as density functions and draw lines and ask, well, what does GD1 prefer? So before doing the full MCMC, we'll just literally draw a line. So here's a few like representative models with the actual 2.3 kilometers per second measurement in black there. And yeah, it turns out, as it seems to be going with CDM is like all that you need, it seems, to do this sort of thing. In this particular model, I have a lot of caveats that I would be happy to talk about for this, but for a first sensible pass, using literature estimates for like the progenitor mass of GD1 from direct n-body simulations, dynamical age, things like that, this is where you end up. And we can look at what this constraint gives us in this mass function plot. This is marginalizing over the subhalo concentration. All that we're doing is changing the amplitude of this. We're not yet allowing for the slope to vary. That's the next step. So technically there is a constraint in here on like warm dark matter, but have not run it yet. Again, visualization that CDM, a little bit above, a little bit below, are very much okay to explain this velocity discrepancy. It's nothing unusual. So like I said, that's a first pass. The next step that I'm looking into is trying to make this all work with more sophisticated stream models and potential models eventually as well. But all of the generative stuff I've been talking about here has been based on generating streams in this test particle sense where you release particles from the Lagrange points of a cluster. Maybe that is not the best way to do it. We want to use more accurate stream models to convince ourselves that the density variations and the velocity dispersions that we're measuring are not due to bad stream models, but are due to actual external factors. So the way to be safe is to use direct n-body. So I've been using the PTAR code. Unfortunately, I never know which way to pronounce it. Combining it with Stream Sculptor, which is the fancy name for all of this perturbation stuff. It's on GitHub, so you're free to look at it and use it. It's kind of fun, all written in JAX and GPU accelerated. But all of the perturbation theory models are like very flexible. You don't have to use a particle spray model to treat these subhalos perturbatively. So we've been working with direct n-body streams and linear perturbation theory to get really good baselines for what an unperturbed stream should look like, and then paint on the other perturbations on top. Surprisingly, I think I made it through everything I wanted to say. So here's like the summary of 3 things that we talked about. Any questions I'd be happy to take. Thanks.
So I think we have almost 20 minutes for questions. And also people on Zoom, if you have questions, feel free to type it in the chat box because we have some sound problems. So if you type a question, I can read it out to the speaker. So yeah. Yep.
I don't know a ton about this work, but I guess that solid streams are usually identified kinematically for membership. So is there a concern that when you measure the radial velocity dispersion of the things you identified by their kinematics that you're missing that high radial velocity end?
Such a good question. Yeah, yes, absolutely. The good news, it's good news and bad news, but the good news is that this is a generative model. So if you have like, I do this actually in those plots, I think. If you have like a 2 sigma deviation, say, I'm going to clip that from my RV dispersion measurement. Don't include it, it's gone too far away. So there's ways to try and handle that systematic. But yeah, it's a concern for sure, I think, and we'll have to be careful and do some like blinded test to make sure we're getting the right answer. Yeah.
Great talk. Going back to your slide in the last section showing constraints from different dark models.
This one.
The one for that,
That one.
this one with like the for fuzzy dark matter.
Oh, sorry. Yeah. This one.
I was just curious, yeah, do you have any plans to extend this to models that enhanced substructure, mostly self-interactive?
Yeah, definitely. That would be great to do. And the good news is the whole code base and formalism is set up where like, if I was given dm, which is something you can fit,
Yeah.
then you just get the rates out. So that is definitely of interest for sure. Haven't done it yet though. Yeah.
I'm curious for the contra constraints,
Mhm.
how sensitive is it to how you parameterize the screen?
Yeah.
We found when you think derivative lines.
Yeah.
That looks
it's-
similar and still.
Yes. Let me see, I don't know, do I have the bonus slide on that? So, yeah, using splines, like I said, the regularization is the hard part with this method. 4 knots, that's all that's being used here. 4 like equally spaced knots in phi1. I've tried 9. 9 gives you wider error bars, unsurprisingly, it's consistent. So I'd say the error bars are sensitive, but the median, like posterior medians look pretty robust. Yeah, so that is the modeling uncertainty that would be good to fold in probably here.
No, I think we have one question online from Carl. Does your derived shape and tilt of the galactic halo relate in any way to the orbit of the LMC and galactic wake?
Yeah, for the LMC point, dynamically, you wouldn't really think that GD1 is being severely perturbed by the LMC. If the LMC is like on its first passage and 50 kiloparsecs and GD1 is within 20, they don't get super close. Impulse approximation says it shouldn't be super important. But the main giveaway, I think, is the lack of velocity track misalignment for GD1. That makes me think that the LMC is not influencing these constraints, though, of course, maybe those are famous last words. I need to think about better ways to like test that robustly. For the halo wake, I'm not sure. It's an interest, that would be a fun interpretation. Where Nand and I were talking about fitting multipoles to this accelerations and seeing what comes out. So maybe that would be one way to test something like that, but unsure so far.
Any other questions?
That's fast.
Yeah. I think if not, we can thank the speaker and.
Thank you.
Yeah, well, if you are okay with uploading the talk, it will be online within a day or two, and I can send the link around as well. All right, thank you so much.
Thank you.